Assalamualaikum. My name is Eizzaniq Binti Azhar. My metric number is AN180049 from Faculty of Engineering Technology. So for the PSM1, I will present to you my research, which is to analyze the soil deformation pattern of underground tunnel of MRT Putrajaya Line by using PLAXIS 2D. So here are some of the overview of my presentation. I will start with introduction, followed by literature review, methodology, expected result, and conclusion. For the introduction, I will start with background study. The disturbance of surrounding soil which caused by tunnel excavation due to the construction of the subway, this process is unavoidable. As a result, how to estimate the ground surface movement is a concern by engineer. Finite element method or finite element analysis is the best method to approach the ground settlement and deformation due to the tunnel design. This simulation is used to provide a structural analysis of how a particular model or design would react under stress in the real world. Within a mesh, the simulation breaks down the entire model into smaller elements, thus the engineer used to test how the different elements of a design interact and perform under simulated stressor. This study investigates the effect of ground movement and the soil stiffness in soil due to the tunnel excavation in different types of ground conditions. The methods that are used to predict and calculate the ground movement by performing a parametric study via finite element method using PLAXIS 2D, version 21. For the problem statement, field observation and empirical or semi-empirical solution have long been used to design underground structure, such as a tunnel, but this solution has never been comprehensive in terms of factor and the parameter affecting such a structure and the surrounding ground. So the main problem for this research I include the effect of groundwater level in different depth during tunnel excavation, the consideration of soil stiffness that can affect ground movement in different ground conditions, the effect of settlement at great depth in different ground conditions during tunnel excavation. For the objective, the aim of this study is to model the deformation of soil that cause ground movement during tunnel excavation. The specific objective of the study that need to be achieved. First, to investigate the factor of deformation pattern of soil change in groundwater level and the different soil stiffness at certain depth during tunnel excavation. Second, to analyze the deformation pattern of soil using finite element method. Third, to validate the result of tunnel model for deformation pattern of soil with the key parameter, which is the changes of groundwater level and the different soil stiffness at the certain depth. For the scope project, I will be investigate the factor of ground movement during tunnel excavation at a certain depth, which is between 10 to 55 meter. By using PLAXIS 2D, I will build a soil modeling using the hardening soil with small strain and the more color model. For the significant study, during tunnel excavation using TBM in Putrajaya Line will cause the ground movement that could potentially affect the building structures utilities at the ground level. So the purpose of this study was to investigate the factor of ground movement during tunnel excavation, including the groundwater level and the soil stiffness at for the different type of soil using PLAXIS 2D. Now I proceed with literature review. In this section, I will share with you the factor of ground movement due to tunnel excavation from the previous study. Selby states that the magnitude of the ground movement is related to many factors such as soil properties, structure properties, construction sequence and workmanship, and excavation geometry. As the geometry around the opening start to move, the changing stress within the vicinity of the tunnel directly affect the ground movement. It is important to estimate the effect upon the structure when the tunnel drive past below an existing structure, but the free ground deformation are not simply to be imposed upon a structure because the structure contributes to stiffening of the ground. Some of the factors that I have included for of the ground movement is groundwater level. Groundwater is a fresh water that soaks into the soil and is held in in pore between rock and soil particle. A major concern in tunnel excavation is unexpected encounter of high inflow of soft ground. Drag a large amount of material by water inflow may cause phase instability, collapse, chimney formation, and surface subsidence. The issue caused by this inflow are often ascribed to the presence of hydraulically conductive fracture or fault when using TBM. A high water inflow drags soft material that increase permeability and connectivity with the rest of the aquifer, producing further water inflow and the sediment drag in a process that grow the intensity. Groundwater will follow its natural course and exert hydrostatic pressure in the most inconvenient place. To estimate the groundwater inflow rate into unlined rock tunnel, the engineer practice depend on analytical method. The location of the groundwater level and the permeability of the rock mass are the two key governing variables. Groundwater has an impact on any excavation job that takes place below the water table. It has an impact on the facility functionality and design, as well as the building cost. In many locations, groundwater-related activity are strictly restricted. So next factor is soil stiffness. Zamani and Motahari state that the release of pre-existing stress upon excavation of the opening caused the soil or the rock to deform elastically at the very least, which common to all opening. The rock will not deform in elastic manner if the stress around the opening is not high. Understand how the soil or rock surrounding a tunnel deform elastically in response to change in stress is critically for solving the subsurface engineering issue. The change in deviatoric soil stress around the tunnel is substantially more than the mean effective stress during excavation, although the shear stress deviates with strain because the soil stiffness is frequently nonlinear. The greatest soil strain caused by twin tunnel contact during tunnel excavation and consolidation may cause more soil softening than when two single tunnels are superimposed. The next factor is tunnel depth. Xiao state that from the previous study by Franzius extend the work of Port and Edinburgh by considering both the geometric parameter together with the building parameter. Variation in building width and tunnel depth they discover that can cause scatter in modification factor, particularly for construction with low stiffness. To reduce the exponent of the building width employed on the original formulation, they suggest to use tunnel depth directly in the expression for relative bending and axial stiffness. Concrete lining facilitate flow by provide a smooth surface and protecting vehicle utilizing the tunnel from rock fragment, while small tunnels are commonly lined by pour concrete into hole drill from the surface. Most rock tunnels require concreting totally within the tunnel due to their great depth. So the final factor of the ground movement is settlement in soil. So the settlement caused by the excavation of the cut will be restricted to a distance equal to the cut depth. If the excavation is made in sandy soil, the structure built near the excavation will be affected, resulting additional settlement. When a cut is constructed in a soft clay stratum, the structure loaded on the side of the cut acts as a surcharge. As a result, beneath this surcharge, the clay near the bottom of the cut yield laterally toward the excavation. As a result, the soil above yielding clay begin to settling. So for the example, we can see is the Leaning Tower of Pisa, construct in 1174, notable example of such a disaster. The tower is 179 feet high with an offset that presently measures 17 feet. Despite extensive repair to stabilize the soil on which the foundation was built, the offset continued to grow at the rate of around quarter every year. So I will continue with the methodology of this project, which will start to study with the factor of the ground movement due to tunnel excavation. I'll divide it into three: tunnel depth, groundwater condition, and soil stiffness. And then I will continue to do soil modeling using PLAXIS 2D version 21. which include the parameter key, which is change the water level and soil stiffness at a certain depth. And then for the data analysis output, I will get the settlement in soil and subsurface, also force exerted to the tunnel, and then proceed with discussion and conclusion. For the parametric study, the key of the parameter are the level of the groundwater condition and soil stiffness at a certain depth. For the modeling, I will be using PLAXIS 2D version 21 to simulate the soil behavior and to determine the influence of the soil properties during the tunnel excavation. So the figure below is the step to execute the finite element tunnel for soil stiffness and the groundwater analysis. So first, I will start with define soil stratigraphy. I will separate 4 layer soil profile with 13 meter of soft clay, 2 meter of fine sand layer, 5 meter depth of loamy, and 2 meter of sand layer. So both table, as you see, is the material property of soil that I will be put in my soil modeling. And then I will start to define the tunnel. I will be setting the tunnel radius to 2.5 meter, and the tunnel design is set material parameter for TBM, lining, and the building. So the table below is the parameter material that I will be insert in my model. After that, I will generate the mesh. I will proceed to the mesh mode, which default a global coarseness parameter to medium. So for the calculation, I will activate the tunnel lining for the initial phase, and next activate the building, followed by the circular plate, which represent the TBM, and then I will activate the TBM conicity, which represent the effect of the cone shape of TBM, which is the cutter head larger diameter than the tail. As a result, the second calculation phase, there is some settlement of the soil surface, and the tunnel lining shows some deformation. So this chapter will detail the method used to meet the study objective and analyze the problem. This model will create with the same goal, which is to replicate ground deformation as well to examine the impact of soil parameter of tunnel excavation. Next, expected result for this research. The TBM will give effect in ground movement that could potentially affect the building, structure, and utilities at the ground level. The purpose of this study was to investigate the effect of groundwater level and soil stiffness due to tunnel excavation in different types of ground condition. As a result, the parameter of water level and soil stiffness description and assumption during tunnel excavation will investigate. From the data analysis, the researcher able to discuss the effect based on the parameter that has been stated. For the conclusion, in this study, a parametric study was conducted based on the key parameter including groundwater level and the soil stiffness for tunneling design at the specific depth to the soil modeling in order to validate the result of two material model, hardening soil with a small strain and the molecular model. Due to the fact that it is still PSM1, no data analysis of the tunnel model has been done. To achieve the goal of the second and the third objective, the researcher will undertake a true study in the future. So this is the Gantt chart project of final year project 1 and final year project 2. Thank you.